So apologies this morning. You were only getting Nathan. Burchin had a scheduling conflict. I was hoping to have the scheduling conflict and send her, but we had to flip a coin. So today I'm going to talk about Zahner as an architectural metal company, and our group, Burchin's my co-lead in the R&D department. We will refer to ourselves as the labs. We kind of use this to sort of describe some of the work that we do. And that we're a small group, and so we're very opportunity costs are high, and so we think a lot about. We like to occasionally try to think about blue sky in terms of a little bit of what we're dreaming where we can go, but we kind of have to tie projects to the research projects to real projects in order to get them kind of funded and keep them moving along. Since we're a relatively small company based out of Kansas City, and we have a satellite facility, but in Texas, but we do work across the globe. Most of our work is here in the States, on both the coasts, significantly concentrated. And I'm just going to kind of run through a few of the projects if you haven't seen our work, but we're an architectural metal company, 125 plus year old. We've done work spanning multiple scales and types of projects, the De Young Museum, San Francisco, the Contemporary Jewish Museum, the Broad Art Museum by Zaha Hadid, recently the Google headquarters, and also SoFi Stadium, the cladding panels on that project. One of our first projects that sort of launched us, and we're kind of known for the exploration and in geometry and pushing material, which we find sort of fascinating in this realm of working within metal as kind of the medium and the domain in which we explore and try to understand how we can push geometry, but also gain the sort of understand the timeless qualities of it. This project that's ongoing, this is the original photo of the Air Force Academy in Colorado Springs. It's a renovation. We're taking off because of the building enclosure has been compromised. It's a renovation, taking down the cladding and recladding it back to an enclosed system. But one of the ideas that how can we engage with existing buildings? But coming back to the base material that we explore of metals and their unique properties that we're continuing to explore and understand how we can exploit further, that we're kind of enamored by the ability for them to have unique properties that are indefinitely recycled, but also last over a significant period of time. Some materials lasting hundreds of years. Diving a little bit more into my group with Burchin, with Zahner Labs. We deal a lot in this realm of moving between digital and physical. It's the kind of thinking about how do we actuate information into material, and how do we actually retrieve that information or get more information about parts. So we think about getters and setters in a lot of our projects that we'll talk about in terms of the notion of frameworks, of how we deploy them across building projects that actually go through. One of the parts that we deploy is early in sort of design components, that how do we chase and kind of find each project has a unique sort of fitness field. If you remember back to sort of Galapagos and some of the tools, where I think we're always sort of chasing the design parameters and design intent, and how do we maintain that high fidelity while still navigating sort of costs and quality to execute on a project. And so we look at this in terms of how can we bring design for manufacturing early, and some of that involves us being involved early, but oftentimes in the process, fabricators are involved late. And so those decisions are, by necessity, that you're going through options very early. But we're interested in how do we build tools that we can push upstream. They're separate from us in terms of needing our involvement, but to where that they can inform designers and how do they decisions affect downstream processes. So these start to target this fitness field in terms of for each project, thinking about how can we give, some of these are simple things in terms of design for manufacturing constraints, of thinking about trucks and what fits on a sheet of material and what's your utilization on that material, to minimize kind of the impact of waste, even though all of the fall off and waste are ultimately recycled, you reduce that amount of energy that's in the material. And then you can also understand how your material, your where you land in terms of project costs. So this is a relatively new area of thinking, how do we build tools that we extend out that are separate from an engagement directly with us, but tools that can kind of live in the wild, to give feedback early on to projects to help navigate them towards an area to where, if you're considering using metal in the different expressions in a facade, that you can understand what range it's going to fall in, so that those ultimately don't get value engineered out or go out for other reasons. One of our other predominant works of research at the group is robotic frameworks. We think about this as these frameworks as sort of general tools that can be deployed on, or a general kind of set of capability that can be deployed on projects. So this one, really we think about these robotics being applied in terms of how do they augment the human component of, we work with a local sheet metal union. And so their expertise in craftsmanship is a part of a long history and tradition. And so how do we think about how can we automate in some ways the boring things away from their part of their job, but allow them to still have significant involvement and allow for that specific tacit knowledge and on-demand knowledge that's been built up over years to execute without the barriers. So a lot of this ends up a focus on positioning problems in terms of how do you locate something in space? How do you deal with compound planes and rotations? And so this being a problem space where we find robots very useful. So one of the projects is assisted welding. We have a large number of things that go through our shop in terms of that come in at unique angles. And previously we used a large amount of jigs and kind of work to get to those angles to be able to facilitate that unique geometry, but started integrating the robot into a process to be able to hold those parts and bring them into the unique conditions. And this looks like very sort of quick prototypes. They build up over time of cardboard studies, kind of following an incremental level of investment. Again, we're kind of testing to see how valid these processes are, and then we're trying to deploy them towards a project in terms of watching for those applications, and kind of guiding them towards what makes the most sense and what's that proper balance between the experience and the difficulty of the task. And once they're there, other things can start to be deployed. We can introduce additional quality control, scanning processes that help us augment the process further and reduce additional waste from it in terms of additional material and control requirements. Also looking at material and how we augment just the finish. So every material that we deal with in terms of from a metals has an oxide that's developed on it. So we're looking at how do we control that oxide development through selective applications, we call it selective patina, but developing a set of typologies and understanding what those growth patterns start to do in terms of directions and the way that we can develop that together, and how do we engage with designers to sort of tell its story through the surface of the material. Maybe kind of skip on this one. Skipping didn't work. But this development is across series of materials, but sometimes both additive and subtractive, but it's how can we set trajectories from a raw state of material, and then how that engages over time. And then how do we engage with designers through design tools such as Rhino Grasshopper, other computational tools to sort of author what that offset and story ends up becoming. Kind of see the idea is that you start with a sort of a raw state and a differential here on steel and aluminum, and then over time you'll always see that offset, even though it'll grow. Material still grows the protective layer, but it now is a unique imprint. Some of these other things that we end up looking at in our group is how do we continue to reduce or augment some of the novel components of looking at mycelium packaging, but also how are our systems not going into the local ecosystem in terms of the patina chemicals that we use. They're part of a closed system in terms of recycling, so none of that material goes off site. Thinking about the actual alloys that we're doing and how do we steer clients towards and inform them of components such as lead, and other additional potential hazards. Thinking about the purity and the life cycle of the material as well. The fact that metal can be fully recycled and infinitely recycled unless it's extensively composited, in which we tend to stay away from. One of the other components right now is the software frameworks, and this being a bit of a broad term, but an area of focus of a platform that we've worked towards. Thinking about this problem of as you move towards the construction end and parts are real, they're on the building, they're going on the building. All the time that you were able to kind of analyze and look upstream and spend with computational tools and have access to it, you lose so much of that as you move closer towards real parts as they go on the building. There's a lot of different efforts to kind of bring that downstream, but this was the particular area where we saw an opportunity. So this looks like a platform we call SurveyLink. It's a web application that we developed to stream positional data from a robotic toll station that the installers have on site. So usually in the form of a tablet, a phone. We've played around with headsets, although AR headsets are a little cumbersome still for the install crew. But the idea is that they can use this on site to get real positions of where parts are. Here you can see the station operating. It's able to follow prism equipment. This station can also kind of double in terms of scanning. It also allows for, since it's in a browser, for multiple stakeholders to be in the same place. And so now whenever installer runs into an issue, engineers can jump on the call at the same time and see and kind of work through. So we're reducing the amount of waste that's spent in the field, waiting, delayed on information to come back from an analysis or an evaluation. So these provide feedback in real time by streaming positional data. This works through a process of aligning our digital fabrication in terms of parts with interface jigs that we deploy on site to be able to coordinate the digital and physical. I kind of go through a case here for a minute of how that works, but what this gives us is starts to give us more information than just position. It can also give us orientation about parts in the field, so that we're not just locating something in space, we're also giving it its compound position, helping us expedite that process, reduce the number of jigs and time and equipment that's deployed there, and sits to where that we can expedite that installation. Here's on the left the chapel project, its current state. It's been remediated down to just the steel, but this is the installer has positioned all of the anchors on that steel that can rotate and move along pipe over 6,000 positions that they have access to in the basket with the station set up. Talk kind of quickly about a project that we have ongoing where this is also deployed to kind of give a little bit more of a study. California Science Center that's ongoing right now. It's actually out there a few weeks ago. But the Space Shuttle Hall enclosure that we're cladding our systems. And this looks like, to give a little bit more of a sense of what this system does, there's the initial component where we're scanning the steel, but then we're using that to align our fabrication models, and not just the whole model, but the in-context parts to update positions, to update locations. And then that's what drives the model position, the web model position that we give to the installer. So these look like outriggers and parts that go up on the building where our unitized system is going to attach to. We get scans back and we segment those into interface points. We're specifically looking at kind of simplify the problem and decouple the concerns on the global scale of the building, because we're really looking at how do these parts interface with each other. Additional software that we've been working on to analyze the point clouds and generate updated positions and information, flagging components, and being able to understand before we're deployed how we need to adjust parts. Again, kind of thinking about this critical components, this interface jig of how we actually get this information. So here we've got a component that gives us 3 points that we index against the outriggers, and we can get a plane. So now we can get compound positional information. So this is what the tablet interface ends up looking like. Is the left-hand side is that feedback information, and they can control the station from there. And the right-hand side is a digital set of directives. So there's no paper directives involved here. This is all about how to give them information that's simple enough for a person up in the basket. I just need to move this thing over and rotate it. And then I want some feedback in terms of where it goes. But now it's leaps and bounds over. Before you were just kind of guess and checking, but now you actually know, and there's kind of a lot that's illuminated through this. But what this results in then is we measure parts in the as-built conditions. We measure parts in our shop and getting precise understanding of where those interfaces are. And then we can test fit them ahead of time, so that whole problem of costs that dramatically go up. So when there's any problem, you've got things that are sitting around and just wasting time, wasting material, go away to where you can expedite installation schedules. One final thing, if I've got a few minutes, we did this year. There was an interesting exploration that we're curious to continue to look at. Is we went to a workshop for Robart, and for it we were able to explore new geometry in a panelized system. And so here we looked at auxetics, the ability to do more with less, and being able to open up, take a sheet of material and then pull on it and expand that material over a larger area and get more from a smaller amount. Series of studies that we did. These look like sort of digital simulations where we're trying to understand what that material behaves. So this is an ongoing component of where we're interested in how could we take a smaller sheet that gets set on site and then is deformed to a larger, and how does it start to perform in terms of its texture and material? Does it look like a fabric? I'm also really interested in this notion of like these parts can be typical parts up until the moment where they're deployed and become unique. So they go through a manufacturing process and are treated, and you get certain economies from that, and then you only make them unique whenever you need to. So the typical, an anchoring system that's all typical parts or set of families, and then a panelized system that we formed on site with a robot. That's my last slide. Thank you.